If you remember, we also discussed a particular reaction which looks very simple, H2 plus Br2 both in gas phase producing hydrogen bromide in gas phase, but the rate law, observed rate law, was fairly complicated, and the rate that was observed, which is half dHbr, we can write the rate in terms of the products like this. Here there is only one product, HBr, which was K2, K prime. K prime is one of the rate constants, and if you remember that it was something like 1 plus K double prime HBr into Br2 minus 1. So this is fairly complicated rate law, the observed rate law, which doesn't follow, it suggests immediately that the reaction did not happen like one H2 molecule and one Br2 molecule just came and collided together to form HBr. Then the rate will be very simple. Then the elementary step is just bimolecular collision, and the rate will be just some observed rate law times H2 concentration times Br2 concentration. It will be as simple as that. But since the observed rate law is very complicated, so people studied this reaction and devised a mechanism. Now what happens, this reaction actually proceeds to something known as radical pathways. So here radicals are generated, and these free radicals are extremely reactive. Radicals means there is no lone or bond pair of electron. There are bond pair and lone pair of electrons, but in addition you have an unpaired electron. That's why it is called a radical. Now these are, by the way, neutral radical. It's not cationic or anionic radical. So what you have to have some step which actually initiate the reaction, initiate the radical reaction. We call that first step as initiation, where this bromine molecule actually collides with something. That something we're writing as M. We'll come to that. What do you mean by M? And then this is step number 1. Then it forms actually 2 bromine radical plus M, and these bromine radicals are also in gas phase, plus M, which is gas phase. Now that M can be any species, so basically it's a collisionally activated dissociation of bromine 2 into 2 bromine radical. It can be a bromine molecule itself, it can be the hydrogen molecule itself, sometimes it can be also the wall of the container. So it says that somehow some of the bromine in the reactive mixture, so in the reactive mixture initially had bromine and hydrogen, and then it is initiated by actually the free radical, which is the bromine radical. Now you could think also that the H2 also breaks and forms H radical, but the bond energy of H2 is much higher. It is much more difficult to break an H-H bond than to break an Br-Br bond. So the first step is basically initiated by the bromine radical. Then once this bromine radical is initiated, it can react with hydrogen gas, and it can abstract a proton from it, and then it can form HBr, which is the product, plus it forms the hydrogen radical. Now any radical species is very reactive, as I said. Now this hydrogen radical can also, in the very same way, these are all gas phase species, react with the bromine molecule and abstract one bromine atom from HBr and give bromine radical back. So you can see that one radical Br is generating the other radical, and here also the H radical is generating the other radical. So this process will continue because you are regenerating some other radical which actually regenerates back the old radical, and this continues. So this is something like a chain reaction, and it just amplifies itself, and in the process you form HBr and you just consume H2 and Br2. So this step is known as the propagation And then you could also have inhibition, in the sense you could think that sometimes these radicals are actually trapped, and one of the trapping will be if the product HBr actually traps, say, a hydrogen radical in the system to form H2 and bromine radical, or this product HBr can also trap a bromine radical and then giving rise to bromine molecule plus a hydrogen radical. Now, as I said, this is known as inhibition, and you can easily see inhibition means these two steps, propagation was these two steps together, and you can easily see that this HBr now actually is basically forming, or HBr, the product which is HBr, is actually inhibiting the process. It is actually scavenging the radicals H and Br, and that's why you see in the rate equation HBr comes in the denominator. So too much higher concentration of the product HBr can also cause the inhibition. So that is a hint that HBr is causing inhibition for this reaction to propose this mechanism, because in the observed rate law we see that it is HBr comes in the denominator. So then also you have a termination reaction, which will be just opposite of the first reaction, where basically two bromine atoms in presence of a third body actually gives you Br2 plus M. Now you can argue that this is, the probability will be very less. Of course it will be very less because it's a three-body collision, but the point here is that when the two bromine atoms collide there and form a bond, then some energy is released, and there should be a third body to take up that energy. So that's why you considered a three-body collision here. Exactly, it is not like a three-body collision like we said, that it is not possible to have a three-body collision and form something like A plus B plus C going to product, and we said that we won't consider this kind of elementary reaction because they are not possible. However, here we are saying a slightly different. It's a bimolecular reaction. It's two bromine atoms forming bromine molecule, but the released energy has to be taken up by a third body, which is not a reactive species here. It is just there, which is absorbing the energy. It may be the wall of the container also. So it is not like that there are three reactants forming product. It is just there are two reactants, they are forming product, but the third body is just absorbing the excess energy. Now also we can simplify further in the sense that this particular reaction, this equation number 5, it is actually endothermic in the sense that it needs heat to be supplied to for this reaction to happen, and this heat is pretty substantial. For endothermic reactions, remember that we always use a positive sign because heat is required for this reaction. So it is energy supplied from the environment to the surrounding. That's why it is a positive thing. Versus this other inhibition reaction is exothermic, which means heat is released by 70 kilojoule per mole, and the first one, the fifth one is basically the other inhibition reaction, which was endothermic by 170 kilojoule per mole. Now, endothermic reactions under normal condition is very, very unlikely to happen because you need much more heat to be supplied. So we can also right away from the beginning ignore this step. So we basically have on average we have total 5 steps. Now you can also put some rate constant for each of these steps. I write K1 here and K2 for this step, K3 for this step, and this reaction is nothing but the inverse of the reaction 2. So we can write the rate constant as K minus 2. For this reaction K minus 3, but we are anyway not going to consider this one. And for this reaction eventually you can write as K minus 1 because it's just the opposite of the first reaction. So now let us devise make a rate law based on this mechanism using the steady state approximation of the intermediate radicals, and the radicals are hydrogen radical and bromine radical. And you see that what is the rate of the reaction, by the way? So the rate of the reaction is expressed as half dHbr dt, and that is wherever you have the HBr dt. So HBr is formed in this reaction, so step number 2, so it will be K2 times Br into H2, and it is also formed in step number 3, which is K3, that's why I'm writing a plus sign, into H into Br2, and plus we see that it is consumed in step number 4. We have ignored step number 5, so we'll use a minus sign. It is K minus 2 HBr into H. So we can write it here. It's minus K minus it will be minus 2 into H2. Sorry, it will be HBr into H. HBr into H. So we see that in order to get the rate law, we have to know what is the concentration of Br and what is the concentration of H radical. Now we'll use the steady state approximation for these two intermediates and see what happens. Now first let us consider the H radical. So we'll say that this dH dt under steady state is 0, which is, now dH dt you can easily figure out where it appears. It appears in the second equation, it is consumed in the third equation. So the second equation was bromine reacting with H2. So it is K2 bromine into, sorry, it will be bromine radical into H2 minus, we have K minus 2, or we can first write the K3. You see the third step, it is consumed H into Br2, H into Br2, and then see where it appears again. So it appears again in reaction number 4, where it is again consumed by action of HBr. So reaction number 4 at a rate constant K minus 2, HBr into it was H. Alright. Similarly, we can write dBr dt under steady state is 0. Now bromine appears in many places. So the first step, which is bromine 2 plus M, it is formed. But then see the first reaction, it is bromine 2 plus M forming the 2Br into M. Now let us just write it here. It is 2Br plus M. If I write the rate of this step with respect to bromine, I have to write half dBr dt is bromine 2 into M. So which means dBr dt will be 2 times bromine 2 into M. Now we are only writing the dBr dt terms. We are collecting the dBr dt terms. So you have to multiply it by 2. So just keep that in mind. So this half actually we are taking on the other side. So which means it is 2 times K1. This would be K1. Sorry, K1 into Br2 into M. And then we have, let us see the reaction number 2. Reaction number 2 will be, it is consumed, so it is K2 into Br into H2. Reaction number 3, it is again regenerated, which is K3 into H into Br2. I'm just following the hydrogen formation reaction. Wherever actually hydrogen radical is generated, bromine radical is consumed, and vice versa. And then you'll have a fourth step, which is basically hydrogen and hydrogen bromide reacts. So then bromine must be formed there. So it will be plus K minus 2 into HBr into H. And the fifth step we ignored. And the sixth step will be just nothing but the reverse of the first step. And you can see here the sixth step. So it is basically bromine is consumed, but so the rate law will be Br square into M. So it is consumed, so it will be K minus 1 into Br squared into M. Now you can first see what is the solution for H radical from this equation, so that will be easier. So see here where H appears, so H appears here, H appears here, and before that you can first solve it as H radical or Br radical, whichever way. So let us first simplify this. Now look at this part, minus K2 plus K3 plus K minus 2. So this is just negative of this part, and this is already 0, so the negative of this part will also be 0. So what we can write using the first basically this is from the H equation or hydrogen radical equation, we can just remove this entire part, and then we can write 2K1 into Br2 into M minus K2 minus K minus 1 Br square into M, that is equal to 0, because this part which I have underscore here is also 0 because of this. Now you can simplify it and get the expression for bromine. So you can just put this term or this term on the other side, and then you can easily see that the bromine square will be nothing but equal to, or we can just write it like this for the typing, K minus 1 into bromine square into M, that is nothing but 2K1 bromine into M, and this M now cancels, so that's why you wrote it as M, because it will not appear in the rate equation. It can be H2, it can be Br2, it can be wall of the container, it can be one of the radicals, so it's just a collisionally activated process, and this is just a third body. And then we can actually see that the bromine steady state concentration is nothing but twice K1 divided by K minus 1 into bromine, the square root of everything, but I'm just writing the rate constant separately and the concentration of bromine separately. Now you can use this, so this is basically the expression for bromine that we need to solve the rate of the reaction, because in the rate of the reaction, remember, both the concentration of bromine as well as H appears. Now we also need to solve the H equation, so we can right away write it from here. So we see that the steady state concentration of H, if we just take that thing common, we can write it like this. So we see that K3 into Br2 plus K minus 2 into HBr times H is nothing but K2 into Br into H2. Br already we know, we'll just replace the value of Br here. So hydrogen atom radical concentration will be nothing but K2 into Br, and then instead of Br we are writing it as twice K1 divided by K minus 1 to the power half. So it is K2, and this is basically we're writing right now. Br expression is this times Br2 to the power half times there is a H2 concentration here divided by this entire thing, which is K3 Br2 plus K minus 2 HBr. So we see that this is the expression for steady state concentration for hydrogen radical. So this is for bromine radical, this is for the hydrogen radical. So we got these two terms, which is looks fairly complicated, and then we have to now solve the dHbr dt, which is the rate of the reaction. So let us now solve it. What is the dHbr dt? So for that you just see this reaction. What is the expression for dHbr dt? So that will be or half dHbr dt. Let us just write it. So half dHbr dt is nothing but half times, let us see what we wrote here. It is K2 Br into H2. It is basically that step 2 it is forming, step 3 it is forming, and then it is consumed only in one particular step, which is reverse of step 2. So let us write K2 Br H2 and K3 H Br2. K2 and we have Br into H2, that is basically reaction of bromine radical which is generated in step 1 with H2, and then the third step, which is basically the generated H radical from reaction 2 is reacting with bromine, and then it is decomposing in step 4, if you remember this one. So HBr and H. Step 5 we ignored, so it will be K minus 2 into HBr into H. So that's the overall thing. So we have to write or insert the expression for the bromine. So it is half times. Now bromine, let us see what is the expression for bromine. It is 2K1 to the power half divided by K minus 1, and bromine it will be Br2, sorry, the 2 should be inside, Br2 to the power half. So let us write it. K2 times 2K1 divided by K2 to the power half, Br2 to the power half into H2. So that is basically the expression for bromine. And then we have H, we have to write. For H, we can actually take it common, so we have K3 into Br2 minus K minus 2 into HBr. That entire thing multiplied by the concentration of H. Now the concentration of H is this, let us write it, K2 to K1 divided by K1, K minus 1 to the power half. It was K2 and it was K1 by, let me just see it one second. It is K2, 2K1 divided by K minus 1 to the power half. And then you had Br2 to the power half divided by 8 into H2. Into H2, not divided. And then you had a division by K3 Br2 plus K minus 2 HBr. Alright, let us go back and just check the equations. So here for the bromine steady state equation, if you remember the last step, which is here, the step number 6, there actually 2 bromine atoms are generated. So again from the same logic, like it is basically half dBr dt for the step number 6, just like step number 1 had this half factor, is minus K minus 1 into bromine square into M. So there will be a 2 factor, so there will be a 2 here, so which means it will be 2 into this, so this 2 will cancel, so there will be no 2 here. And for the similar expression for hydrogen, there will be no 2 here, so it will be just K1 by K minus 1. So here there will be any 2, here there will be any 2. Now how to solve this thing? So you can see that this entire expression K2 into, we can actually just take common for this part, so it is half times K2 into K1 by K2 to the power half into bromine to the power half into H2, and inside parentheses you have 1 plus, so you have taken this part common, this entire part common, which I am writing in the first bracket. So this and this taken common, so this I have 1 plus, I'll have K3 Br2 minus K minus 2 HBr divided by K3 Br2 plus K minus 2 HBr. So then I can just proceed with this. So this will be nothing but if I just add these two, K3 Br2 plus K minus 2 HBr, and so it will be K3 Br2 minus, sorry, plus, because I'm just multiplying by 1, K minus 2 HBr, so that term will cancel, we can see it, plus K3 Br2 minus K minus 2 HBr. So this term cancels with this term, so we'll be left with twice K3 into Br2. So that 2, let us write it, so this will be nothing but times twice K3 into Br2 divided by K3 Br2 times plus K minus 2 into HBr, and it is be multiplied by this entire thing, half K2 K1 by K2 to the power half bromine to the power half and H2. You can see that we are almost close here. So the rate of the reaction, so this half and half will cancel, and what we see here, we can actually divide the numerator and the denominator by Br2. So we can just rewrite it. So what we got, half dHBr dt is, let us just arrange the constants, which is k2, k1 by k minus 1 to the power half. Then we have Br2 to the power half H2 divided by, we are dividing both sides, and there is also an k3. Remember, there is a k3, so we can write it as k3 into k2, and then we have or we could actually divide it by not only Br2, but we could divide the numerator and denominator by k3 into Br2. So then this factor becomes 1 plus, we'll have k minus 2 divided by k3 times HBr, and there is also a Br2, so that will be Br2 to the power minus 1. Yes, I think we're correct. Yeah. So this is the rate expression that we saw, that we observed experimentally. As we see that if it is even if it is a fairly complicated rate expression, we can actually express the entire thing. This will be actually Br2 to the power half, because no Br should come in the rate expression. And we can see that this observed rate, which we had started with, we could recover. And here, so the k prime is nothing but a combination of constant, which is k2 into k1 by k minus 1 to the power half, and the other constant, k double prime, the way we have written it at the very beginning, it will be k2 divided by k3. So as we see that we can actually get the mechanism of this reaction very, very correctly by assuming that the reaction happens through the radical pathways. And there are some hints from the observed rate law that HBr is coming in the denominator, which means actually HBr acts as an inhibitor. And also you see that this nice arrangement here of this or the nice analogy that we had developed throughout, using also a fact that this is an endothermic reaction, so this elementary step we discarded. And finally, by using all this thing and going through all this exercise, we discovered that yes, actually the reaction follows the observed rate law, and not only that, the rate constants also can be recovered. The observed rate constant, there are two rate constants, k, which we wrote as k prime and k double prime. They are also described as something like a combination of the rate constants of the elementary steps, which is k1, k minus 1, k2, k minus 2, and k3. So we will one more thing we can see here. So we can see that all the rate constant k2, k minus 2, k1, k minus 1, and k3, they appear in the rate equation. Only thing is that k minus 3, which is the reverse of this, which is the endothermic reaction, that doesn't appear. It is obvious because we ignored it. So to summarize, we saw that how a very simple looking reaction, H2 plus Br2 is giving you 2 HBr, can have a very, very complicated rate law, but we can actually devise a mechanism which satisfactorily explains the observed rate law under steady state approximation of the intermediates, which are very much reactive intermediates, which are hydrogen radical and bromine radical. So now we are all set to discuss the catalysis part, but before that we'll first consider or we'll first discuss the unimolecular reaction, and then we'll discuss a little bit about the Arrhenius equation, and then we'll follow the enzyme, then we'll have a discussion on the enzyme catalysis.